everyone. In this video, we're going to talk a little bit more about how to classify monosaccharides. So, some questions to ask when you're classifying a monosaccharide is the monosaccharide an aldehyde, aldose, or a ketone, ketose? Also, how many carbon atoms are in the monosaccharide? So if you have 3 carbons in your monosaccharide, we would call that a triose. So notice that we have that OSE ending for monosaccharides. If you have 4 carbons, it's called a tetrose, 5 pentose, 6 hexose. So these are good to know for this chapter in particular. So as an example, looking at the monosaccharide on the left, we first want to identify, is it an aldehyde or a ketone? So we're going to look at the top, and CHO indicates that we have an aldehyde. So that's just the abbreviated form. So we would start by saying aldo, and then we're going to count the number of carbon atoms. So we have 1, 2, 3, 4. So there are 4 carbon atoms in this monosaccharide, so it is a tetrose. So putting it all together, this is an aldotetrose. Now on the next monosaccharide on the right, looking at the top, we have a ketone. So we start by calling this keto, and then we count the number of carbon atoms. 1, 2, 3, 4, 5. So we would call this a ketopentose. Okay. Now, most monosaccharides are aldoses, meaning that they contain an aldehyde. And almost all natural monosaccharides belong to the D series. And we talked about that previously. Humans can only really metabolize D isomers of monosaccharides. We also previously talked about how the maximum number of possible stereoisomers is 2 to the n, where n is equal to the number of chiral carbon atoms. Now, half of those stereoisomers are going to be D isomers. The other half will be L isomers. So looking down below, we can start to kind of figure out the pattern that occurs with monosaccharides. So for instance, if a monosaccharide has 3 carbon atoms, we call that a triose. It should really only have 1 chiral carbon atom. So for instance, it might look like this. So there's only 1, 2, 3 carbon atoms there, and only one of those carbons is a chiral carbon. So that means we would only have 2 to the 1 or 2 stereoisomers. So one of those would be the D isomer and the other would be the L isomer. Now let's just go all the way to the bottom of this chart. If we have 6 carbon atoms in our monosaccharide, we would call that a hexose. 4 of those would be chiral carbons. So that means we would have 16 stereoisomers. So half of those would be the D isomers, half of those would be the L isomers. So we'd have 8 of each. Now, why does this occur? Well, if we start with our triose, again, we only have 1 chiral carbon, so we would have 2 stereoisomers, and one of those would be the D isomer. Now, let's say we add on another carbon onto our chain. So now we have the tetroses. And notice that when we add another carbon on, we're going to see two more isomers because we could either have the OH on the right or the left when we add that extra carbon into the chain. So now we have two chiral carbons. So that means we would have four total stereoisomers, and half of those will be the D isomers. So two of them are D isomers. And remember, we determine D or L based on this OH group that's kind of second from the bottom there. So if it's on the right, then it's a D isomer. Now we can keep going. So notice here that we're just adding more carbons into our chain each time. And when we do that, we have a couple of options. Either the OH is on the left or the right. So we're really just kind of creating a map here from the previous samples on the last slide. And then you can keep going and going and going. So every time we add a new carbon, we're actually adding two more isomers into the mix. Now, most monosaccharides are called sugars because they taste sweet. And all carbohydrates are solids at room temperature. Because of the multiple OH groups on our monosaccharides, they can form hydrogen bonds with water molecules, and therefore they're really soluble in water. So down below, we have a table showing the relative sweetness of different sugars. So lactose, for instance, has a relative sweetness of only 0.16. And if we compare that to sucrose, which is table sugar, sucrose has a sweetness of 1. But you could have even more than that. So fructose, for instance, has a sweetness of 1.73. So that's kind of like that fructose corn syrup that you might hear about. And then you can see that these other sugars kind of fall in between that range. All right, so let's talk a little bit about monosaccharide reactions before we go on to the next video. So all monosaccharides that have at least 5 carbon atoms or more exist predominantly as cyclic structures. And we would call these hemiacetals or hemiketals depending on if you started with an aldose or a ketose. So down below we have Haworth structures for different sugars, galactose and ribose. And this can be used to depict the three-dimensional cyclic structures. So notice in galactose, we have our hemiacetal there. And then ribose, we also have a hemiacetal. Okay, so we talked about hemiacetals and hemiketals before. So if you want to go back and review that information, you can. But again, remember previously we said that a hemiacetal looked like that. So we've got two excuse me, that should be just an alkyl group on the left. So there should be an OH group on the top and an OR group on the bottom, as well as a hydrogen. And on each of these structures, there is an invisible hydrogen attached. So that's our hemiacetal. So how do we go from that open chain form of the monosaccharide to the cyclic form of the monosaccharide? Well, what happens is we're going to number the carbons starting at the top and going all the way down to the bottom. So in the structure up above, this is glucose, we have 6 carbons. Now, the OH group on the second to last carbon is going to attack the carbonyl carbon, the number 1 carbon. So that is going to create a 6-membered ring. And in particular, notice that the oxygen in the OH group ends up in the ring as one of the 6 members. And then we have carbon 1, 2, 3, 4, 5. And notice the CH2OH group is kind of considered a group coming off of the ring. So that goes up above. And then don't worry too much about the other OH groups for now. That's not as important for this class. Now, this ring structure is called a pyranose ring. So it's a 6-membered ring containing an oxygen atom. Now, this is another way to view that same cyclization of glucose. So notice again, we're just kind of wrapping the open chain around into a ring structure. And then the OH group on carbon 5 is lining up with the carbonyl group on carbon 1. So that's going to create new bonds. So the oxygen on carbon 5 will line up with the carbonyl carbon. And then the hydrogen on that OH group is actually going to add to the oxygen on carbon 1. Now, there's a couple different ways, or a couple different products we could get here. We could end up with this new OH group either pointing up on carbon 1 or pointing down on carbon 1. So that carbon is going to determine the stereochemistry of our molecule. So we're going to call this an anomeric carbon. So carbon 1 here, which is right next to that oxygen in the ring, that is our anomeric carbon. And we'll talk a little bit more about that in a bit. So the former carbonyl carbon is now chiral and is called the anomeric carbon. Now let's look at an example of a 5-membered ring that forms from, for instance, fructose. So fructose has a ketone at the top instead of an aldehyde. Now, we're still going to have that second to last OH group attacking the carbonyl carbon. So this is going to give us a, let's see, 1, 2, 3, 4, 5 membered ring, where again the oxygen in the OH group ends up in the ring, and then we've got carbons 1, 2, 3, 4 wrapping around. And then our CH2OH group on the bottom is pointing up on that last carbon in the ring. And we also have the CH2OH group from our ketone, and that's going to be on carbon 1. So this is actually a hemiketal instead of a hemiacetal. Okay, now the ring that forms in this case is called furanose. So it's a 5-membered ring containing an oxygen atom. So here's another view of that same cyclization. So we've got our OH group that was on the second to last carbon, and it's lining up with the carbonyl group in the ketone at the top. So we're going to form a bond between the oxygen and carbon, and then hydrogen and oxygen. Now, similar to what we saw before, you can end up with 2 different products here. One where the OH group that we're forming points down and one where it points up. So again, that carbon 1, the carbon that used to be the carbonyl carbon, that is going to be our anomeric carbon. Now, because that anomeric carbon is chiral, there's two possible stereoisomers that can form during cyclization, as we saw with glucose and fructose. So we call those alpha and beta anomers. So those two stereoisomers are alpha and beta anomers. The alpha anomer has an OH group on the anomeric carbon that points down. The beta anomer has an OH group on the anomeric carbon that's pointing up. So this is just a way to distinguish between the two different stereoisomers. So instead of D and L, we call it alpha and beta. And the actual definition of anomers, anomers are stereoisomers that differ in the 3D arrangement of groups at the anomeric carbon of an acetyl, ketyl, hemiacetyl, or hemiketyl group. Now, in our case, we're really looking at hemiacetyls and hemiketyls. So let's go back and look at glucose again. So let me just clear the pen markings here. So we saw that we could either have a ring where the OH group is pointing up or pointing down on the anomeric carbon. So again, if it's pointing up, we call that the beta anomer. If it's pointing down, we call that the alpha anomer. Now let's look at the fructose stereoisomers. So again, we had a situation where the OH group was pointing down. So we call that the alpha anomer. And we had the other situation where the OH group is pointing up. So that is the beta anomer. All the other groups stay the same, so it's really just this anomeric position that changes. All right. So when you're looking at a Haworth structure like these, what you want to do is draw the ring with its oxygen to the back. So if you have a furanose ring with 5 members, the O will be at the top, and then you can just draw the rest of the ring from there. And usually what I'll do is I'll draw the oxygen and then just make some dots for the other carbons, and then I'll just connect the dots. Now, if you have a pyranose ring, a 6-membered ring, you put the oxygen in the back, and then you can just draw some dots for the other 5 members of the ring. And then we're just going to draw a hexagon here. All right. Now that CH2OH group that's always at the bottom of our Fisher projections, that will always point up. And that's going to be on the carbon right next to oxygen. And then the anomeric carbon is always to the right of the oxygen. Okay, so I know I just gave you a lot of information here, so we'll stop the video at this point. Next time we'll talk a little bit more about monosaccharide reactions now that we know more about the cyclic structures, because some of these reactions do occur with the cyclic structure. So I will see you then.